Let's look at some more polar graphs. Consider the equation r equals the sine of 3 theta. When theta is 0, 3 times 0 is 0, and the sine of 0 is 0. So there's the point 0, 0. When theta is pi over 6, 3 times pi over 6 would be pi over 2, and the sine of pi over 2 is 1. So we're already all the way out at 1. What happened in between? Well, like when theta was pi over 12, 3 times pi over 12 would be pi over 4, and the sine of that is square root of 2 over 2. And once theta gets past pi over 6, like when theta is pi over 3, 3 times pi over 3 would be pi, and the sine of that is 0. So we're all the way back to 0. What happens as we go past pi over 3? Well, then 3 theta is going past pi, and the sine of that is getting negative. So like when theta is pi over 2, 3 times theta is 3 pi over 2, and the sine of that is negative 1. So that gives us this point down here. Remember, when r is negative, we're going backwards. So if we face in this direction but take one big step backwards, we get to this point. So this loop down here gets traced out as theta itself goes from pi over 3 to 2 pi over 3, because then 3 times theta, which is what we're actually taking the sine of, is going between pi and 2 pi. And that gets us back to 0, and then as we keep on going, we get this third loop. We end up closing that loop when theta itself is pi. And then if we let theta keep on going, we just get those 3 loops again. So this kind of graph is called a rose curve, and this particular one has 3 loops, 3 leaves or 3 petals on the rose. What do you think would happen if we changed the sine to a cosine? R equals the cosine of 3 theta. Well, we still get a rose curve with 3 loops, but it's oriented differently. It's turned sideways. One of the loops goes out here, and then the other 2 are here and here instead of going down and like that. And that's because with cosine, if we start with theta being 0, the cosine of 0 is 1. And then by the time theta gets to pi over 6, 3 times pi over 6 would be pi over 2, and the cosine of that would be 0. So we get the same loops, they just happen at different places, at different angles, different thetas. So polar coordinate equations that involve cosines tend to be symmetrical with respect to the x-axis, whereas equations involving sines tend to be symmetric with respect to the y-axis. Now, what do you think would happen if we changed this 3 to a 5? R equals the cosine of 5 theta. Well, if you guessed we were going to get 5 loops, you were correct. We have a rose curve with 5 loops. What if we do r equals cosine of 7 theta? Yes, that's right, 7 loops. And they do get skinnier, but we do have 7. If we went around and traced out all the loops, they would all happen as theta went from 0 to pi, and then from pi to 2 pi, we get the whole thing again. What if I change that 7 to a 4? Ha, fooled you. You thought there were going to be 4 loops, didn't you? But actually, there are 8 loops. This time, if we just let theta go from 0 to pi, we would get 4 of these loops. But then we let theta go from pi to 2 pi, we get the other 4, so we get 8 of them in all. So the trick is, if that number in front of the theta is even, we get twice that many loops. Whereas if it's odd, we just get that many. And what if it's not a whole number at all? What if we do something like the cosine of 3.4 theta? Well, then we get a bunch of overlapping loops, and we have to let theta go from 0 to, I don't know, maybe 10 pi or something like that to get all of those. But we get this interesting pattern here. So you might want to try some different values of the number in front of the theta and see what you get, what kind of different patterns you see. Okay, how about this one? R equals 1 minus 2 times the sine of theta. Let's look at a few points. When theta is 0, the sine of 0 is 0, 2 times 0 is 0, 1 minus 0 is 1. So here's the point where theta is 0 and r is 1. Then as we go around and theta goes from 0 to pi over 2, the r's are getting smaller. They're going down to, well, the sine of pi over 2 would be 1, 2 times, or yeah, 1. But before we get to pi over 2, let's look at what happens when we are at an angle of pi over 6. The sine of pi over 6 is 1/2. 2 times 1/2 is 1, 1 minus 1 is 0. So by then we're down to 0. And if we keep on going to like pi over 2, sine of pi over 2 is 1, 2 times 1 is 2, 1 minus 2 is negative 1. So in here, these are the thetas between pi over 6 and 5 pi over 6, and the r's come out negative. And then once theta gets to 5 pi over 6, r is back to 0 and starts getting positive and gets bigger and bigger and bigger. And the biggest it gets is when theta is 3 pi over 2, because the sine of 3 pi over 2 is negative 1. 2 times negative 1 would be negative 2, and then 1 minus negative 2 would be 3. So as we go around, we have this inner loop that happens when r is negative, and we have this outer loop that happens when r is positive. And this particular kind of curve is what's called a limacin. It helps you to remember that. Think it looks kind of like a lima bean. So you can have a limacin that has one of these inner loops, or you can have one that doesn't. That's just kind of dented, but just goes all the way around. So if you look in your book, they have a little chart showing you some of the basic kinds of polar coordinate graphs. You can have a limacin with an inner loop, or a dimpled limacin that doesn't go all the way to the pole, but kind of goes in a little bit and gets a little dimple. You can have a convex limacin, and that depends on the relative sizes of the numbers a and b, when you have a plus or minus b times either the sine or the cosine of theta. We've already talked about these rose curves and the difference between whether n is odd or even. There are equations that give you just a circle. There are equations that give you a lemniscate, sort of a figure 8 kind of thing. Now let me say something about the homework for this section. Part of the homework will involve matching equations to graphs. So on Canvas, I have posted a document that has a bunch of graphs on it. And what you'll be doing for some of the homework is looking at the equation and figuring out what does the graph of that equation look like. It's going to look like one of the graphs on this page. You have to just tell me which one. Like, is it C1? Is it A3? Which one is it? And then as an extra credit assignment, this is not on the assignment list, but I'm adding it as an extra credit part to the homework assignment. Play around with graphing some polar equations and see if you can come up with some interesting looking graphs. And if you find any that are particularly interesting, that you really like, especially if they're different from some of the ones in the book or the ones that I've talked about in this video, go ahead and share them with us. Now, the way you can share them is I'm going to set up a discussion board on Canvas where you can come in and post about the polar coordinate equations you've come up with. And if you make them in the online version of Desmos, here's one way you can share them. When you've got an equation that you like, say cosine of 3 theta plus 2 times the sine of 2 theta. Okay, that's a little bit interesting. Let's say I want to save that and share it with other people. So I can click this little icon up here that says share graph, and it gives me a link. I can just copy that link and then paste it into any other document or posting or wherever you want to paste it. So I could go into the discussion board and paste this link, and then anybody else could go in and click on the link and get a look at your graph. So I encourage you to play around with different polar equations, see what the graphs look like, and if you find some that you particularly like, share them with the rest of us.